This lesson is about matrices and systems of linear equations. So first, let's define what a matrix is. A matrix is an organization of numbers into a rectangular array of rows and columns. So a matrix will look like this. This would be an M by N matrix, where M is the number of rows and N is the number of columns. Each element within the matrix um, would be a number. It could be variables, but something like this, a sub 1, 1, those numbers in the lower right-hand corner determine the row and column position of that. So a sub 1, 1 means it's the element in the first column, first row. This one here, a sub 3, 2, means it's the element in the third column, second row. Third row, second column. This one here, a sub 1, 3, is the element in the first row, third column. So the first number in the subscript determines the row, and the second number is the column. So if I said I sub ij, that would be the element in the ith row, jth column. So here's an example of a 3 by 3 matrix. The number 5 is in the third row, second column. The second one is a 2 by 3 matrix. It's got 2 rows, 3 columns. This number, -4, is in the second row, third column. Notice that you can have zeros, you can have fractions, you can have decimals, integers. Any number could be an element within the matrix. The third example, this is a 4 by 1 matrix. It's got 4 rows, 1, 2, 3, 4, but only 1 column. And the number 13 is in the third row, first column. Okay, so that's just some examples of how to read a matrix and how to determine its dimensions. You always state the number of rows first, followed by the number of columns, just like that. When the number of rows and the number of columns are the same or equal, we call that a square matrix. So that could be 1 by 1, 2 by 2, 3 by 3. You can state the system of linear equations as something we call an augmented matrix, where the coefficients of the variables and the constants are the elements of that augmented matrix. So here's an example of how to express a system of linear equations as an augmented matrix. So here I have 3 equations. You want to make sure that the variables show up in order. In other words, x, y, and z, just like this one with your constant on the other side. In the second equation, there is no y term, which is fine. And in the third equation, there is no x term, which is fine as well. So the way we're going to represent that is the first equation is written as 6, -2, -1, and 4. 6, -2, -1 are the coefficients of x, y, and z, and 4 is your constant. Sometimes a dotted line is placed between the variable coefficients and the constant, but that's not always required. And then the second equation is written as 1, 0, 3, 1. The 0 represents the missing y term. And then the third equation doesn't have an x term, so that's what this 0 is holding that place, followed by 7, 1, the coefficients of y and z, and then the constant 5. Okay. So in previous lessons, we learned how to solve a system of linear equations, but now we're going to be solving a system of linear equations when it's in a matrix form. And so the methods that we will use require us to understand something called elementary row operations. And that can be done in an order on an augmented matrix in order to solve a system of linear equations. So, what's an elementary row operation? That's when you are adding two um, equation or two rows, or multiplying a row by a non-zero constant, or switching two rows. So you can do different kinds of operations. And this here, if I wanted to add one row to another, this is saying that I'm going to add row I to row j, but I'm going to multiply row j by a constant in order to come up with a new row um, row I. Okay, so the little the number here will tell you which row you are manipulating. Another possibility would be to just multiply a row by a constant. So that could happen. And then you could interchange or switch the order of two rows. So row I, switch row I and row J. So that will be the notation that's used to describe the elementary row operation that we're doing. And that will be important so that you can stay organized and be able to check your work um, and understand how you're changing from one matrix to another. So to solve an augmented matrix, your goal is to get ones on a diagonal from left to right and zeros below the ones, and then use back substitution to solve for the other variables. So the way we're going to accomplish this is called Gaussian elimination, is we're going to use some elementary row operations in order to accomplish that. And what you do will depend on the numbers that are presented to you. Not every one of these will be done the same way. So here is the augmented matrix of that system of linear equations. And so the good news is that I already have a 0 in this position. So my goal is to get ones all here and zeros underneath it. And I already have a 1 in this position. So some of the work has already been done just because of the nature of the system. So what I decided to do was to add row 1 and row 3. When I add row 1 and row 3 to get a new row 3, this term is going to turn to 0 because negative 1 and 1, negative 1 plus 1, will give me 0. So what that means is only row 3 is going to change in the next augmented matrix. Copy row 1 and row 2. They should look exactly the same. But when I add row 1 and row 3 to get a new row 3, you're going to get 0, 0, negative 4, and 4. Okay, so the 0, 0 comes from adding 1 and negative 1. So that's the first 0. Then negative 1 plus 1 gives me the next 0. Negative 1 plus negative 3 gives me the negative 4. And then 2 plus 2 gives me 4. Okay, so that second augmented matrix already looks better than what we started with. And now the next thing I'm going to do is I'm going to multiply row 3 by negative a fourth, and I'm going to multiply row 2 by negative a fourth to get a new row 3 and a new row 4. That means copy row 1 over, should look exactly the same, and just multiply the second and the third row by those coefficients. So row 2 multiplied by a fourth will give me 0, 1, 1/4, and 7/4. And row 3 multiplied by negative a fourth will give me 0, 0, 1, negative 1. So I have all ones on a diagonal and zeros underneath it. That's exactly what we wanted to accomplish when you're using Gaussian elimination to solve a system of linear equations. And now I can solve for the system. So this last line right here tells me that z is equal to negative 1. So that was our first answer. And then I can plug in right here. That second to last row, or the second row, is saying that y plus 1/4 z equals 7/4. So that's what I have here. Y plus 1/4 z, but z is equal to -1, so I'm plugging that in, equals 7/4. So I can solve for y because that gives me y minus 1/4 equals 7/4. Add 1/4 over to the 7/4, that's 8/4, and so y is equal to 2. And now that I know that z is -1 and y is equal to 2, I can then plug in back in here, which says that x minus y, so that's now minus 2, minus -1, because my z is -1, equals 2. So these two give me x minus 1 equals 2. Add 1 to both sides, you get x is equal to 3. So you present your solution as x, y, z. So that's my solution is 3, 2, -1. So you get the same results as if you had used substitution and elimination like in the last section, but this is just another option called Gaussian elimination. Okay, here's another. I'm going to rewrite this system as an augmented matrix. So that's written as first row 1, 1, -1, 0. Second row is 1, 2, -3, -3. Third row is 2, 3, -4, -3. So the first thing I decided to do was subtract row 2 minus row 1 to get a new row 2. So that means row 1 and 3 just get copied over. They should look exactly the same, but my row 2 is changing because I'm subtracting row 2 minus row 1. So I end up with 0, 1, -2, and -3. -2 is because I did -3 minus -1. -3 minus -1 is -3 plus 1. That's -2. So that's why where that comes from. All right, and then I need to go further. Remember, I want ones on a diagonal and zeros underneath it. So I have some of that so far, but not quite everything I need. So what I decided to do was I decided to subtract row 3 minus 2 times row 1 to get a new row 3. So, and that will allow me to get rid of this 2 in that position. So when I do row 3 minus 2 times row 1 to get a new row 3, that means all you do is copy down row 1 and 2. They should look exactly the same. And then only my row 3 is going to change. And when I do that, my new row 3 is 0, 1, -2, and -3. So far, this is what I'm seeing. It's looking better. I need all ones on a diagonal and zeros underneath it. So these two still need to change. So I will need to do another operation in order to accomplish that. So I'm going to subtract row 2 minus row 3 in order to get a new row 3. And when I subtract them, this will definitely subtract to give me a 0 there, which is what I'm trying to accomplish. So when I do row 2 minus row 3 to get a new row 3, I copy down row 1 and 2 right in here. And my new row 3, well, interestingly, everything's going to cancel out. So I end up with all zeros in that last row. And when you get something strange like that, that's going to mean that you have a dependent system. And a dependent system means that you have infinitely many solutions. And so oftentimes you will be told to let z equal a particular variable. And so in this case, I'm going to say, well, let's let z equal a. If z is equal to a, then you can plug in that a right in either one of these. And so that means that y minus 2a equals negative 3. And if you solve for y, you get that y is 2a minus 3. So in other words, your solutions are going to be expressed in terms of a variable because there's infinitely many of them. And now that I know that z is a and y is 2a minus 3, I'm going to plug those in right in here and solve for x. So I get x plus y, which is 2a minus 3, minus, and it's minus because of that, minus z, which is now a, equals 0. When I combine like terms, 2a minus a leaves me with x plus a minus 3 equals 0. And when I solve for x, you subtract a and add 3, so x is negative a plus 3. So now I have my three answers where your x is negative a plus 3, my y is 2a minus 3, and my z is a. So that means for any value that you plug in for a, you get a solution for x and y. So for example, if I said a is 1, then y will be 2 times 1 minus 3, which is negative 1. I didn't need that parentheses there. And my x would be negative 1 plus 3, which is 2. So one solution for this system would be 2, negative 1, and 1. But there's infinitely many of them because this a could be anything. It could be 0, a could be negative 5, it could be positive 100. There are infinitely many answers. This is just one example of a solution that satisfies the system. Okay. Another method which is very similar to Gaussian elimination is called the Gauss-Jordan elimination. Gauss-Jordan is going to take just a little bit longer because it's a very specific format that your final augmented matrix should be left in. So with this method, you're going to use elementary row operations to put the matrix in reduced row echelon form. That means that there will be ones in a diagonal and all other entries above the ones will be zeros. And when that happens, you won't have to do this back substitution to solve for x and y the way I did in the last two examples. So what does a reduced row echelon form look like? It will look like something like this, where you have ones in a diagonal, zeros above it. And so if you end up with something like this at the end, you would say x equals 2, y equals negative 3, and z equals a half. So the answers would already be right here for each particular variable. But to get it to look like this reduced row echelon form, it means that you'd have to probably do quite a few operations to get it to that point. So here's an example. I have x plus y plus z equals 9, x plus 3y plus 3z equals 23, 2x plus y minus z equals 7. The augmented matrix looks like this, just the coefficients of x, y, z in the first three columns, the constants at the end. So the first thing I decided to do was to subtract row 2 minus row 1 to get a new row 2. And so row 1 and 3 get copied over, and my new row 2, when I subtract row 2 minus row 1, will be 0, 2, 2, and 14, right? 23 minus 9 is 14. And then I decided to subtract row 3 minus 2 times row 1 in order to get a new row 3. So this row gets doubled. If it makes it easier for you to write it out, you can write 2, 2, 2, 18. Otherwise, it might be a lot to keep track of in your mind. And I'm going to subtract row 3 minus row 2, minus 2 times row 1, which is this right here. And so my new row 3 becomes 0, -1, -3, and -11. Row 1 and 2 stay the same, right? You're just copying row 1 and 2. This is just what you're using when you're subtracting. You're not writing 2 times row 1 in the new augmented matrix. You're just using it to subtract it from row 3. Okay, so we're making progress. So far I have 2 zeros here, and I do have at least the first one has a 1 in it. The first row has a 1 in the upper left-hand corner. Okay, then I go on to the next operation, elementary row operation. I'm going to do row 2 plus 2 times row 3. So if I multiply row 3 by 2 and add it to row 2, then this one will turn to 0. And so that's what I'm trying to accomplish here. So 2 times row 3 means that this will become 0, -2, -6, -22, and it's going to get added to row 2, which is 2, 2, 0, 2, 2, 14. Okay, so that gives me a new row 3, which is 0, 0, -4, and these two added together is where the -8 comes from. Okay, so again, it is looking better. So what I'm going to do next is I'm going to multiply row 2 by a half and row 3 by -1/4. And when I do that, row 1 just gets copied over, and my new row 2, when I multiply it by half, is 0, 1, 1, 7. And my new row 3, when I multiply it by -1/4, is 0, 0, 1, and 2. Okay, so right now this is in your Gaussian elimination form, but now we're trying to accomplish this Gauss-Jordan method, which means I still need to get zeros up here. Okay, so in order to do that, I'm going to do the next operation, which is to subtract row 1 minus row 2 to get a new row 1. So row 1 minus row 2 to get a new row 1. And when I do that, these two will turn to 0. So I get 1, 0, 0, 2, and then row 2 and 3 just get copied over, 0, 1, 1, 7, and then 0, 0, 1, 2. So the last thing I need to get rid of is this 1 there. I need to make that into a 0. So the most logical place to do that is to subtract row 2 and row 3 to get a new row 2. And so row 1 and 3 get copied over, and my new row 2 becomes 0, 1, 0, and 5. So row 2 minus row 3 is why that 7 turned to a 5. Okay, so now this last one here, this is Gauss-Jordan form or method. And so I get that x is equal to 2, y is equal to 5, z is equal to 2. And so there is my solution for this independent system, 2, 5, 2. And just like any other system that we've solved in the past, when you get a solution, you can always check it by plugging in 252 into the original equation. So I'll just check the first one, but it should work for all three. If I plug in 2 plus 5 plus 2, that should equal 9. This is equation 1. And 2 plus 5 is 7, plus 2 is 9. Left side equals the right side, so this is a good solution. And the same thing would occur if you plugged it into equation 2 and to equation 3. That solution would work. And I encourage you to try that, just to practice checking your solutions. Okay, so here's another I have x minus y minus z equals 3, and I have 2y plus z equals 2, and I get negative x plus y minus 2z equals 3. So first thing you want to do is write this as an augmented matrix, which is on the next step. And so that's your first matrix here on the left. Then I'm going to add row 1 and row 3 to get a new row 3 that will eliminate that and make it a 0, but it also makes this one into a 0, which is actually very convenient. So row 1 and 2 get copied over. My new row 3 becomes 0, 0, negative 3, and 6. That means that I can immediately take care of row 3 and make it look the way I need it to look by multiplying row 3 by negative a third. That will change this to a 1. So row 1 and 2 get copied over, and my new row 3 is 0, 0, 1, negative 2. Okay, so now I'm going to add row 1 and 2 to get a new row 1. And what that will do is it will make this one into a 0, which is again something we need to do. And so my new row 1 becomes 1, 1, 0, and 5. 5 because I've added these two numbers, row 1 and 2. So again, it's looking pretty good. I need this to have all ones on a diagonal and zeros above and below it. So this needs to change and this needs to change. So next thing I'm going to do is I'm going to subtract row 2 minus row 3 to get a new row 2. And so when I do that, my row 1 and my row 3 just get copied over, but row 2 minus row 3 will leave me with 0 here. 2 still remains, but then these two will give me a result of 0 in this position, which was, again, something that we still needed to accomplish. So again, it's looking better than what it was. And 2 minus negative 2 gives me a 4. Okay, so now, again, that 2 there needs to change in this position. So I'm going to multiply row 2 by a half. So row 1 and 3 get copied over, and row 2 changes to 0, 1, 0, and 2. So I have one more thing that I need to accomplish. I need to make that into a 0. And the easiest way to do that is just to subtract row 1 minus row 2 to get a new row 1. And so my row 1 changes to 1, 0, 0, and 3, because 5 minus 2 is 3. So this is now in Gauss-Jordan form, where I have ones on a diagonal and zeros above and below it. So now you can state your solutions, which is x is equal to 3, y is equal to 2, and z is equal to negative 2. So 3, 2, negative 2 is your solution for this independent system. And again, you can plug in those numbers into any one of these equations to check that your solution works. So if your augmented matrix reduces to a matrix with a row of all zeros, except for a non-zero number in the last column, in other words, your constant is something other than 0, then your system will have no solutions. So I did one example where I ended up with a whole row of zeros, but what this is saying is if you end up with a row where you get 0, 0, 0, and something that's not 0, that's going to be something that cannot be solved, an inconsistent system. So that would be an example of what it would look like. This would determine that you would have no solution for a system like that. All right, so here's one for you to try. You can solve it by either Gaussian elimination or the Gauss-Jordan method. Your solution is 101, so I would like for you to give it a try and see if you can come up with that same answer using either one of these methods. Okay, that's it for this lesson. Good luck.